Thank you. We're getting ready to start the next session. It'll be number S17. This is a breakout session, the impact of data quality on asset management systems. And one of our leading subject matter experts, Siamak, will now proceed. Thank you.
Thank you, Bill. So, good afternoon, everyone. I'm Siamak, and I'm going to talk about data quality in this session. So I think I'll wait 1 minute so that everyone settles down. All right. So just to get to know the crowd, how many of you have been dealing with the quality aspects of data in any way, like supervising, assuring? Cool, interesting. We as the software implementer, researchers, spend a lot of time on implementing cool new analytical methods to process data, to get conclusions from data. We also spend a lot of time on IT aspects of sharing data within the organization, creating reports, which are absolutely essential and important. But I think if the data that is the basis of all these functions does not have acceptable, which we will get to this term, definition of this term, quality, the rest is just, I see it as a fun practice, intellectual exercise, which does not have a lot of practical value. Because when you can't rely on your data, you can't also rely on the conclusions that you make from those data. So I really appreciate you guys attending this session on the data quality. Generally, I think we can pay more attention to the quality of the data. That's an important topic. The problem that I am going to address here is, first, we don't know how accurate our planning is, the results of our analysis. And that's, well, not always, definitely, but that's very common. And in many cases, we don't know what is the acceptable level of quality for our data. Many of our analysis is based on condition data that we collect for assets. That's why I am focusing on assets condition data in this presentation, but there are also other types of data that are important for our asset management system. For example, costing data. For example, our performance models. But here my focus will be on the condition data that we collect. Who cares about this? Obviously, whoever who uses assets condition data for analysis and planning, including transportation agencies. And if we can address this problem, well, who can benefit from it? Obviously, agencies, because they can plan better, they can meet their goals, they can get a higher rate of return on their investments and save money. And citizens will also enjoy having a higher quality network. What the concepts that I will be talking about is applicable to a wide variety of assets. But just to limit the scope of this discussion and having a case study here, I am focusing on pavements. Before getting into the details, I would like to review the definition of a pavement management system. ASHTO defines pavement management system as a set of tools or methods that assist decision makers in finding optimum strategies for providing, evaluating, and maintaining pavements in a serviceable condition over a period of time. The issue of condition data, variability in condition data in all assets, and especially in pavements, because pavements is, pavement management system is probably one of the oldest asset management system, has been studied for a long, long time. Here I have already dropped very old quotes on literature, but I have quotes on from since 1994 to very recently. And these are all from very well-respected professors in this topic. You can see some of these quotes are pretty strong. For example, Larson says, a pavement condition data quality can be bad enough to be completely useless. And so this is a very well-known problem, variability in asset condition data, especially pavement condition data. And there seems to be a general agreement in the literature that this problem exists. However, less work has been done to quantify the problem and how we can address it. But why? Why are condition data have a lot of variability? Well, again, in the literature, several factors have been mentioned. In the case of pavements, shape and condition of each pavement section, bias toward detecting higher severity distress while missing lower severity ones. Like in other words, we tend to miss the smaller cracks. Also, automated data collection techniques have the same issue. Many of these events don't detect the smaller cracks. The the collection method, if we are using a windshield collecting, or if somebody's manually collecting the distresses, or we're using a van, it can introduce variability to the data. Weather condition, direction and the angle of sunlight, if we collect the data once in the morning, once in the afternoon, the results can be different. And so on and so forth. Let me back up a little bit here. What is data quality? Does any of you guys want to define data quality?
Yes, fit for use. Is the data fit for use?
Mm-hmm.
Trusted.
Mm-hmm. Very interesting, yeah. Yep, there are several different definitions for data quality. There is not a standard definition for it in the literature. But accuracy, precision, and completeness are the most frequently mentioned aspects of data quality. I'll start with accuracy. Accuracy is generally defined as the difference between a measurement and the true value of that measurement. Lack of accuracy can cause small deviations, small errors, or extremely big errors that we call outliers. It is possible there are some techniques to detect these outliers, and it is very useful to detect. It's very important to detect them because even though they are low in numbers compared to the bulk of data that you have, they can have a very important, significant impact on your statistics. But the small deviations are very difficult to catch. In the case of asset condition data especially, even the definitions of a true value is ambiguous and subjective. So if you pick two raters, two very experienced raters, send them to rate a pavement section, they might come back with different answers, different ratings. And that's because even the definitions of, for example, different types of cracks has overlaps. So accuracy in the case of asset condition data has not gained much popularity. The next aspect of data quality is precision, which is often defined as the ability of a process to repeat the same accurate measurement over time. In other words, you repeat your measurements, how close your recordings are. This is a very popular quality measurement for asset condition data, and some people believe that precision is even more important than accuracy in the case, because if you calibrated your decision-making process based on whatever data you have, you're used to it, you know its consequences. Regardless of how accurate it is, you know what you get. So many of the data quality assurance techniques in this area is focused on precision. Like a very common example of it is that you collect original condition data on your pavement network. Then you collect audit data on a certain portion of your network. You calculate difference between original and audit data and compare that difference with a data quality target that you define for yourself. For example, one of our clients has this data quality target. 95% of collected data to have an absolute deviation of less than 10 points out of 100 between audit and original data. If the vendor brings brings back the condition data that fit within this criteria, they accept it. If not, they need to redo the data collection. Any of you guys or your agencies uses a different method for quality assurance of condition data?
I think one of the things to clarify is, why set those limits on the target?
Why?
Why? Yeah, no, in terms of quality, what are you using the data for?
Exactly.
Are you trying to determine average network condition, or are you trying to build performance models? Because quality will have two different, sets of measures depending on the need.
That's absolutely true, yes. When we are talking about quality, it definitely goes back to what is the purpose of using our data. If we are measuring a length, we can, it depends if we need just a rough estimate or accurate to the third digit, decimal digit, and it all depends on what is the purpose of it. And I'll get back to that thing in future slides. But yeah, this is I think the most common way of making sure that the condition data has the quality, and I haven't seen much different methods.
One other method is you could use panel surveys as well to average out multiple raters looking at the same section, collecting the same data and then averaging those results. That'll be closer to your ground truth than just one rater and one sample.
Exactly, and that's
I've seen that done before as well.
like for a research purpose,
Yeah,
or
on research or special studies.
yeah, because I just can't imagine it's going to be very expensive to have a significant portion of the network rated multiple times by different people, right?
Even two people, right?
Yeah.
If you average out, two values as opposed to one value, you'll be closer to what the truth is, or three.
Right.
Yeah.
It's definitely
I've seen
closer.
that done too.
Mm-hmm. Interesting. Okay, so in this study, our objective is that assess the impact of that data quality target that I just showed you an example on the output of PMS. And the output of PMS here is the purpose that we just talked about. We used two of our clients' pavement management systems and databases that I refer to them as PMS1 and PMS2 here. And as the pavement management system output, I picked the needed budget. Obviously, a pavement management system can have several different outputs. And I defined the needed budget as the minimum budget needed to keep the weighted average condition index of network above 85, while not allowing more than 5% of the network length to be in poor performance level. You could have defined different objectives for your analysis, but I think this is one of the common ones. And so that the algebraic aspect of it can be done, we had to make some assumptions about distribution of the error. So I assumed that the error in original and audit data are normally distributed, and they have the same distribution. The same standard deviation, basically. So let me explain the framework of the pavement management system here. This is pretty consistent throughout all the clients that we have, so many of you might already know the framework. First, we get inventory, inspection, and other kinds of data that you use for decision making. If you're looking at a multi-year analysis, you need performance models. In other words, a mechanism to tell you what is the expected condition of your asset in future years. Using those set of models, you come up with the predicted performance data. Our first client, PMS1, uses exponential performance models, and our second client uses linear performance models. And once we have all the existing and future performance data, we need to assign the right treatment to each of our assets. And that is done mostly using decision trees or decision matrices based on the factors that are often include functional class, pavement type, last treatment type, condition indexes, and there are different variation of condition indexes that are used between the different agencies. And we often don't have enough money to do all those repair actions that we picked. So we have a project selection phase at this phase. And it is an integer-based optimization method where you pick the work plan or set of projects that minimizes or maximizes your objectives while meets all your constraints. I refer to that as the optimal work plan. And once we have our pavement management system set up, we run an analysis using our our condition data as they are and get the needed budget. Then we introduce error to it, artificial error to it, and recalculate everything, come up with the needed budget, again continue repeating this iterative process with different levels of errors. And we'll see how the needed budget changes with the level of introduced error. So here I want to share the results of this simulation. I have a graph here. On the horizontal axis, we have level of error, which is quantified in terms of standard deviation of the normal random error that is added to the condition data. And on the vertical axis, I have the impact of that error to my PMS output, which is defined in terms of error, mean absolute error in needed budget. The error that I'm adding here is a random error. So it's a probabilistic function. I run it once, it gives you one result, one set of results. You run it again, it gives you a different set of results. So we repeated this analysis several times, and what you see here is the average of those results. For first line, PMS1, this is how I interpret the results. If I add 5% standard deviation of, if I add normal error with the standard deviation of 5%, I'll get almost 25% of error in my needed budget, my defined needed budget. And as you can see here, it's the pattern is very linear. The second client also follows the same pattern, almost linear, but with a much higher sensitivity to the error. So the first maybe conclusion is here that different pavement management systems, different asset management systems can have very different levels of sensitivity to errors. And that's not really good or bad. It's just important to know the level of sensitivity of your system to adapt your condition data to it. So I talked about one of our clients' data quality target. 95% of the collected data to have an absolute deviation of less than 10 points between audit and original data. It can be shown statistically that this is equivalent to having an error of standard deviation of 3.5. If I plot it on the graph, it will be, for the first client, it will give around 15% of error in needed budget. In other words, if they use that data quality, they should expect as high as 15% of error in their outputs of their pavement management system. For the second client, if they use the same example target, they are looking at having as high as 50% of error in the estimated needed budget. Well, probably, I'm just guessing that the 50% is a little bit too high, and it's not an acceptable level of error in the estimations. So they might want to look at a tighter and more conservative data quality criteria. Well, so I changed this instead of 10 to 5 this time. 95% of the collected data to have an absolute deviation of less than 5 points between audit and your original data. It can be statistically shown this is equivalent to having a standard deviation of 1.7. I plotted on the graph. So this will be, this time, the first PMS is going to get maybe 5% of error in the needed budget. And the second one is going to get around 25% of error. Again, they can ask the same question. Is 25% of error acceptable in the needed budget? If not, they will need to spend more money or effort to increase the level of accuracy in their results. So, what do you guys think? Do you think what is the acceptable level that can be tolerated in outputs, level of error that can be tolerated in outputs of the pavement management system? Like 25%, is it fine? Or
there's a lot of variability in the pavement data that is competitive. So I cannot set the kind of standard that's very, very tight, and that's kind of variability in the data will exceed that tolerance. So we have right now almost 90% with 15 points in the score. So you have 95% at 5 points.
yeah,
And look how much error we get.
yeah. So it's even more relaxed than this
More
criteria.
relaxed than this.
Yeah. Do you think you can have higher accuracy in your data if you revise your distress collection manuals or different techniques or anywhere?
Right now, we were doing windshield survey, and I feel like the tolerances that we have are very reasonable. There is a lot of variability in windshield surveys. I cannot put it in kind of something like this in windshield surveys. We're switching to automated, so I'm charting into new tech, we're
show.
Yeah, no, Siamak, this is a great concept, and I'm glad you brought it up. Because where we've taken this is that you're looking at probably a combined distressed index, or
Yes.
maybe a combined condition index. What we actually did is looked at the different distress types. And maybe longitudinal cracking has the highest variability as opposed to, say, transverse cracking or alligator cracking. And it's based on how you model and put those together. And so you can actually take this another level and actually model based on standard deviation of, one distress type or several distress types. And it's a sensitivity analysis.
It is, exactly.
And then you can focus in that, well, maybe for longitudinal cracking, we need, more information and want to be more precise. So great slide right there. And, it's a lot of work, but it is just part of, building that into the models and, validating them over time. It's so easy to collect data, but again, what's the data and what's the quality, what's the variability, and then breaking it down into components. Same thing with roughness, right? You do the same kind of analysis on that. So it's a great slide.
Thank you. And can you share the conclusion that you made out of that analysis? Like, did you think that you already have the acceptable level of quality in your data?
Well, I think a lot of it has to do with maturity and how comfortable and how well you know the process. For instance, sensor data, IRI is probably one of the more mature data types that are out there that's been collected for probably, 15 years plus with some pretty decent standards. But when you actually come to like collecting data off video, certainly the technology has improved in that area, but when it was, a visual type survey off video, there was a lot of variability, shadows, is there a crack, is it a moderate or severe crack, what's the width, measuring lengths, repeatable, and then, you're collecting vast amounts of data along the length of a road length. But, what we found is that as you start doing this, data quality improves. So it's one of these necessary exercises that when I was at Virginia DOT, we did that and quite successfully really improved the ability of using the data to model performance. That's what we identified as our target. We want quality good enough that we can see a year-to-year meaningful difference over time. Because you're trying to build performance models out of this, and
Right.
ultimately, the analysis that flows from those. But this is actually how we stepped into it.
Can you say a little bit more about how you compute that percent error? You might have said that, and maybe you didn't get it, 10% or what?
The vertical axis?
No, the horizontal.
There's a horizontal axis.
Yeah, if you've got, does that mean if you've got a rating scale of up to 5, then 4.5 and 5.5%, 10% error, how do you actually compute that?
So our condition indexes were on a scale of 0 to 100. So that's in that scale. So it's like, for example, 10 out of 100. So in your case, it's going to be out of a scale of 5.
So this was a Monte Carlo type simulation? Then?
Yes.
Yeah.
Did I answer your question?
Yeah, you did. Process.
Yeah. So it's an integer 0 to 100, and we added a random error, normal random error, and the normal distribution has two parameters, like the average and the standard deviation of it. The average was 0, and the standard deviation is these numbers. And for example, the 10% means that the standard deviation was 10 because our condition index was 0 to 100. Okay, so maybe.
In reality, that could be a pretty big difference. If you're like on a 0 to 5 scale, that 10%, you right on that?
Yeah, it's a very very, very big number. Yeah. I think it's 60. If you're assuming your distribution is normal, it means 67% of your data are within 2 standard deviation plus minus of your average. So in this case, we are saying 67% of our data are between, can have plus 20 or minus 20 error in them, which is pretty big. I don't expect we have that level of error. We should probably be around in that range. We did the same analysis in multiple years, so we multi-year analysis. And one observation that I found interesting was that the error doesn't just simply go away in future years. Like if you run 5-year analysis, you have a lot of error in the results of your first year, but the error persists during the future planning period. And it also changes direction. So the error in the first few years might be underestimating the budget, and in next years it might be again overestimating the budget. It fluctuates, and it's really a complicated impact. So give you a quick summary of what I said. There is a emphasis on risk management these days. It's part of the criteria of MAP 21, and everyone seems to agree that risk management is very important. I see data quality as one of the risks to this process, to the planning process. So let's say you have a mandate of having not more than 5% of your network in poor condition, and it's part of your funding depends on that. And you plan so that you don't get it next year, but simply just because the data does not have the right quality, you may end up not meeting that need and losing some part of funding that you can get. I'm still thinking about this, but this is like an open, can be an open discussion with you guys. Is it a good thing that your agency, your pavement management system is not sensitive to errors? I was asked that question, and I'm not sure about that. Like, we saw 2 different graphs. One agency had a very sensitive. Being sensitive to data means that your outcomes of your pavement management system depends on the data and is responding to it. So if it was just simply a constant function, it was not sensitive at all to pavement, but it was very unreasonable. So I think the important thing here is that you just know the sensitivity of your outcomes of your system to the errors and plan for having the acceptable level of quality for that. We saw that error in condition data can highly distort the analysis results, and particularly when they happen on bigger assets, more expensive projects, the impact is much higher. Like I've seen, like let's say there's a huge bridge in your network, and if you have an error in condition assessment of the bridge, then you may be off or by a high margin in your budget allocation. So it might be one thing to consider that for larger assets, more expensive assets, you have a tighter data quality criteria. And the last thing is that the error in your pavement management system data or your asset management system data will persist through the planning period. It's going to be there. It's not going to go away with years of having several years of analysis. And that's pretty much all I had. There are still some works that are not done here. I just looked at error in condition data, but there are errors in cost data. There are errors in performance models data. And in one sensitivity analysis we did on error in performance models, we found out that's even more significant. Its impact is even more significant than condition data, because that causes that error is repeated every year in your analysis, because you use your models every year to estimate the future condition. So these errors are also not independent of each other. They interact, and the form of interaction can get pretty complicated. We also assumed here that the errors are normal, while it's not really the case. There are studies out there who assume very complicated distributions. Normal might be good enough to give a back of the envelope estimate, but we can get certainly more accurate here. And that's pretty much what I have. Open it for discussions for you guys. I think we're done.
Thank you.
Thank you.